everyone, I'm Mason. I've been doing an A290 in the lab for the past year, and I've been working on specifically as my research topic, creating safe escape trajectories for binary formations of satellites. So we want to create trajectories that basically help satellites that are in a dangerous position get into a safer position. So I'll take you through the motivation of this problem, how we're going to frame it as a research problem, some supporting work and challenges that are currently faced, how we're going to provide new solutions going forward, and then I will summarize and talk about what we can do from what we have now, and from what I've done up to this point. So let's go into the motivation. I think it's pretty well known among the lab that formation flying and distributed space systems offer some very clear benefits and offer new mission concepts that are very impressive and can do things that single monolithic spacecraft cannot. However, this comes with significant risks such as collision in orbit, which we definitely want to avoid. It is a hazard for the mission as well as all other future of spacecraft. If we create more debris in orbit from a collision, we risk the future of all craft in space. So the lab is working currently on several CubeSat missions and formation flying missions, one of which is VISORS, which will use a set of 2 spacecraft to image the sun with unprecedented resolution, and will be in very close proximity of just tens of meters. So collision is a very big risk in this situation and something that we absolutely want to be able to avoid in all cases. So as I mentioned before, collision is a disaster that we absolutely want to avoid, and how we will go about this is by generating escape maneuvers. So these will be maneuvers, impulsive maneuvers specifically designed to move our spacecraft into a configuration where they are not expecting a collision. So if you're following these graphics, we have 2 spacecraft on a trajectory where we expect them to collide, or we expect one of them to behave unpredictably. We want to be able to generate a maneuver on board the spacecraft, which may have to react very quickly and may not have time for ground intervention, to be able to choose that maneuver and get out of the way so that they do not cause the crash in orbit as I described before. So I'll be framing this problem as achieving what we'll discuss as passive safety between the spacecraft in orbit. And first, I think it's relevant to introduce some of the notions of spacecraft relative motion that we'll be talking about. So an important frame to understand is the RTN frame. So that is represented by a frame centered on the chief spacecraft. We'll have a chief spacecraft and a deputy spacecraft in our binary formation, with the distinction being the deputy is performing maneuvers around the chief. And we'll have an RTN frame, so that'll be centered around the chief, and it'll be a Cartesian frame with the three directions R pointing along the radial direction from the satellite to the center of mass of the Earth, an N component in the direction of the angular momentum of the orbit, and T direction completing the right-hand triad. So that'll be a long track in the orbit. And so this is the notion of passive safety I briefly mentioned before. So when we say we want an orbit to be in a passively safe state, we want it to need no further active inputs in order to avoid a collision. So if our 2 spacecraft are impending a collision, they'll need some sort of action, and then we want, after that action, for there to be no real more hands-on, like the spacecraft don't have to make active choices after that point. They'll be in a state where they can basically say, I'll be safe over the next horizon and I'll have time to kind of diagnose and figure out what's going on. So passive safety can be framed as achieving a safe separation in the RN plane. So I introduced the RTN frame before. We'll decompose it a bit into the RT plane and the RN plane. And this is a convenient distinction to make because the RN plane displays very periodic motion that changes very slowly over time. So I'm showing over a few relative orbits or few orbits of the formation around the Earth. We can see a large change in the along track position, but the RN position is a relatively stable elliptical shape. So in order to achieve this passive safety, we want to achieve a safe separation in the RN plane that will give us some separation that will not be changing quickly, as well as introduce some drift in the along track direction. So that'll allow the spacecraft to get some breathing room from each other, and allow us to hopefully diagnose what is going on and have them back in working order soon. A useful tool for addressing these or describing the relative motion of these spacecraft in the RTN frame is a set of relative orbit elements. These are the quasi-non-singular relative orbit elements that I have here, and they are a reparameterization of the classic Keplerian orbital elements that many people are familiar with, combining the orbit elements of the chief spacecraft and the deputy spacecraft. And as we can see, we can describe the relative position in the RN frame with these relative orbit elements. So that's the expression I have in the bottom left. So we can map the relative orbit elements to the geometry of the RTN motion. And I'm going to show you again here, just geometrically what those orbits actually look like based on these relative orbital elements. So we'll have elliptical motion in the RN plane, you see, and then there'll be elliptical motion in the RT plane, which can drift over time with any relative semi-major axis. And so now I'll talk about what it means to generate a maneuver that will cause the separation and passive safety of the spacecraft system. So when we talk about a maneuver, we want an impulsive velocity command. The impulsive velocity can be broken up and decomposed into the RTN components and a location where we want to perform this maneuver. So that'll be which parameterizes the phase in the relative orbit. In a spacecraft scenario, we want to minimize fuel that is being used in any situation because it is very difficult, if at all possible, to recharge spacecraft. So when we're generating a maneuver, we want to generally minimize the magnitudes of the RTN velocity impulse components. And it has been addressed frequently in literature before to use impulsive velocity changes to achieve specific variations in orbit states or relative orbit states. But this problem is has a little more at play because we have to, we're not looking to achieve a specific orbit, we're looking to achieve a range of orbits which provide passive safety. So that's separation in the RN plane and a drift over time in the along track direction. And we can map the impulsive velocity components to changes in the relative orbit elements using linearized Gauss variational equations, which I'm showing here. And I'll show you how those actually affect the relative orbit elements. So here I've split up the relative orbit elements into three two-dimensional planes from our original 6 variables. And we can see how we can play with them using this impulsive velocity movement. So based on our phase in the relative orbit, that will be able to slide so we'll break it up into the relative eccentricity vector, the relative inclination vector, and the relative semi-major axis and mean longitude, which doesn't have a specific name as far as I'm aware, but we'll be able to manipulate according to where we are in the orbit and according to the impulsive velocities we're able to put out. And this shows basically how we're able to slide around our quantities of our ROEs. So what we have so far in terms of generating passive safe and describing passive safe orbits is there's been work describing eccentricity inclination vector separated orbits. So it is very convenient in terms of the RN geometry to have your eccentricity vector and inclination vector perfectly aligned, so they have the same phase. Here I've split the XY components of each vector into like a phase magnitude form. So if they match in phase, you'll have a very neat and squared off ellipse of easily seen dimensions of the relative inclination vector length and the relative eccentricity vector length in the RN plane. So this sort of design makes it very easy to keep out of a certain area around the chief. So if we wanted to target an orbit that was not getting closer than a certain amount to the chief, so that would be our RN separation, it would be very convenient to achieve a relative, an aligned eccentricity and inclination vector. It is not essential, but this kind of philosophy for designing our relative orbit based on the quantities of our eccentricity and inclination vectors will be a prevailing theme in this work. A work from Adam Koenig and Dr. D'Amico earlier showed that with a relative eccentricity vector and inclination vector, it needs not be directly aligned, of course, but you can actually parameterize a hyperbola where if you can put your relative eccentricity vector inside the green part of this hyperbola, you are in essentially a safe separated state. So this is kind of a big colorful diagram without many units, but if we consider a straight vertical relative inclination vector, these are the areas where you'd be able to put your relative eccentricity vector and still maintain a safe Rn separation. And this can be parameterized by the relative separation you're trying to achieve by this hyperbola inequality over here. So that works exactly with a vertical relative inclination vector, but that is not an important part of the assumption. So I will go into what we have to actually assume to complete this, to work, or what I've assumed up to this point to work on the problem. And that'll be, we're working with near circular orbits. So that affects our linearized Gauss variational equations affecting our control inputs to the problem. We are assuming impulsive control. So that'll be impulsive velocity components. So an instantaneous change in velocity, which is appropriate for these maneuvers, which will happen over very short time frames of seconds, milliseconds, in contrast to an orbit, which will take many minutes, hours, half a day in a low Earth orbit. We will assume that we have our generated delta VR, delta VT, delta VN, which can be oriented arbitrarily in the RTN frame by rotating the spacecraft or by just the sum of components in the RTM frame. And we can achieve an arbitrary orientation and magnitude, which can be achieved practically by just doing several short impulses over a very short period of time. And we will neglect perturbations such as Earth oblateness effects, the solar radiation pressure, while we will keep in Kepler effects, which are important for understanding the drift of the along track direction over time. Okay, so previously I showed you the relative safe states in the hyperbola formulation. So that was for a purely vertical inclination vector. However, can actually be generalized to any inclination vector, just parameterized by the relative phase of the inclination vector and eccentricity vector. So with our non-constrained vertical original true state on the left, we can simply rotate to a frame where the inclination vector is vertical, map our hyperbola of safe states, and then rotate back to our original frame, and we'll have a safe hyperbola in the frame of our original eccentricity and inclination vectors. And so this means we have a target set of states which we can shoot for with our impulsive velocities. Remember, I showed we can move our ROE states with those impulsive velocities in those relative planes. So we will try to target with our relative eccentricity vector a way into that safe space of our relative inclination vector. Alternatively, this formulation works exactly the opposite. If we start with a perfectly vertical relative eccentricity vector, we can complete the same process for an inclination vector and move our inclination vector. So an important note of what I just showed you in the relative safe state hyperbola is it assumes a zero relative semi-major axis. And in our problem formulation, we really desire a non-zero relative semi-major axis so that we can inspire some drift between our spacecraft over time and give them more room to recover. So we need to adapt our understanding of what a relative state space is to give us solutions that will allow us to have a non-zero relative semi-major axis. So we can still use the key fact from the relative eccentricity inclination vector hyperbola was that by aligning them in that hyperbola, you can achieve a separation of basically a keep out zone of a circle around the center point of your orbit in the in the Rn plane. So we can sort of generalize that with a surrogate orbit or auxiliary orbit center that is not at 0 on the Rn plane, but is located somewhere else, and then just have a smaller effective safe area. So starting from a pre-maneuver trajectory where our chief is at 0, 0 in the RN-RT plane, and we have a deputy moving around it. We discover some kind of fault, we predict some kind of collision, we decide we need to maneuver. From this point, we decide we need some relative semi-major axis. So this, I think, would be well designed as part of the mission requirements in the planning phase on what sort of relative semi-major axis you'd want to expect from your spacecraft formation. If it needed to go into this recovery mode. So we can fix 2 of our design variables based on these factors. So based on when we detect faults and what sort of separations we're expecting between our spacecraft. And then define based off those how we are able to maneuver around this auxiliary center. So the auxiliary center is shifted based on the relative semi-major axis, basically shifts up and down in the Rn plane. And that is affected only in our linearized formulation, only by the along track velocity components. That's that delta VT. So this will allow us to create this auxiliary safety zone that is a keep out zone around that X point, which is our effective center of our hyperbola safe zone, which gives us a practical safe zone around our origin point, so around our actual chief spacecraft that is contained within that circle. So this will give us a conservative boundary in most places, but we guarantee that our spacecraft in the Rn plane get no closer than that pink circle. And so this gives us the Rn separation we need above us, which we can specify to be a certain amount. As well as giving us the along track drift, which wasn't previously possible with the relative eccentricity inclination safety. And then once you have your minimum separation, you can construct your hyperbola and move your eccentricity vector or inclination vector into the safe state hyperbola based on this shifted formulation. And I'll show you practically what this involves. So we will compute based on a reconfiguration of our inclination vector, which is affected only by the linear formulation, only by the delta Vn, the cross-track direction velocity. We will compute a phase and an amplitude of the inclination vector after that effect, and we will compute the rotation to bring it into the rotated vertical frame. In the rotated vertical frame, we can express how the eccentricity vector is affected by the impulsive velocity, the delta Vr and the delta Vt. And then we can finally use that expression in our safety hyperbola conditions. So that's this expression here is the safety hyperbola. And using this expression, it will give you this, which is a nasty kind of look. It is not that complicated in delta Vr and delta Vt. It is simply a quadratic expression of delta Vr and delta Vt, actually, which is very handy because if we fix our delta Vt by our drift desired, and we can fix our UM by our fixed fault detection, then we can assume, and we can fix our delta Vn at this point to be just 0, have no cross-track velocity, then we can solve exactly for the delta Vr that we need to achieve this perfect reconfiguration into a safe state. And so I'll show you here, we have our original blue trajectory. We detect some faults. We want to move out of the keep out zone around the chief orbit, and now we have the resulting red trajectory, which stays completely outside of our prescribed, our literal safe zone in pink, or our literal safe zone is in black, and then our guaranteed pink safe zone is therefore also kept safe. So this is just a random-ish original vector, but this this will work for basically any original eccentricity vector inclination vector combination. And this is just the movement in the eccentricity inclination vector state space. So that expression was very unwieldy to deal with, and I'm going to speed up a bit here. I apologize. So potentially we can make the expression simpler to deal with if we relax some of the assumptions about the boundaries. So if instead of using the strict hyperbola intersection, we intersect instead with a cone that contains the hyperbola, we can then have a simpler interaction boundary. So that involves just solving this linear equation below. However, it does not guarantee as much separation because the straight line has no real impact on separation in the Rn plane. We really want to contain that straight line within its own safe hyperbola. So we have a linear boundary along our original safe hyperbola, which is easier to intersect with, but doesn't necessarily give us as good a separation. But it is fully contained within our second hyperbola, which I've introduced in orange. So we have guaranteed safety up to the minimum separation of the orange hyperbola. And then we can compute our change in the eccentricity vector and have safety guaranteed by the orange hyperbola. In order to achieve physical trajectories, you cannot, there is a minimum distance that you can actually specify to shape this cone. And I've derived that analytically by having the cone be tangent to the safe state hyperbola based on the orientation of the Rn orientation of the spacecraft at the maneuver location. So basically this allows you to have an upper bound on what distances you're able to achieve, and you can achieve distances lower than this, but this is the most you're able to achieve using this method. And in practice, in this example, we achieve very good Rn separation based on the linearized boundary method. However, you can see that it is not as tight up against the boundary as the quadratic perfect solution. So this is not fuel optimal, or it does not provide us with as much guarantee on separation as we get with the quadratic model, but it is more flexible, it is easier to manipulate, and it provides a safety margin. So this is the motion in the eccentricity inclination vector plane, showing the movement of the eccentricity inclination vectors, and this shows that we're intersecting with the conic boundary, which is within its own safe hyperbola. So we are guaranteed safety up to the safe hyperbola there. So this is computing the linearized boundaries along an entire orbit with that same initial eccentricity inclination vector configuration. And we are along the whole orbit. The separation of the spacecraft in the Rn plane is showed in blue. The amount of distance we're able to guarantee at each point is shown in red, and the amount of distance that we actually accomplish is shown in the orange-yellow color. And so you see throughout most of the orbit, we're achieving a separation that is much higher than what we're promising. There are some points where we're right against the boundary of giving exactly what we promised, but we're not violating that promise at any point. So what I've tried to do up to this point is provide basically in steps how we can go from a problem of trying to keep the spacecraft passively safe, so give them some distance that they will not intersect at and some along track drift. And then we've been able to cast this as a problem in ROE space and move our problem from the broad provide safety and not get close into a concrete objective in ROE space. So we've done this by using a few conservative approximations of our Rn safety. And by doing so, we're able to compute maneuvers in closed form that achieve this passive safety, but are overly conservative and leave a large margin over what we are able to, over what could be exactly computed. That is, will be looked at further as I go into looking into the robustness to uncertainty in ROE states as well as maneuver execution. So particularly with the quadratic solution, you're computing exact intersections with a stricter boundary, small errors in the maneuver execution may lead to faltering outside of that boundary, or I expect to lead to faltering outside of that boundary. So taking that into account, particularly for the quadratic solution, I think will be very difficult, but the linearized solution is a way to hopefully make that more tractable. You may have noticed before, I kind of hand waved away computing solutions with the delta VN, the out of plane solution. That is because it is a nonlinear term, and when I've found my linear solution, and it is the most difficult to deal with. However, using it would potentially lead to more fuel optimal solutions. So revisiting and trying to look at a more theoretical optimization standpoint in closed form is definitely warranted, because safety is our top priority, but fuel consumption is another large priority for us. This methodology needs to be validated in simulation to ensure that we are matching all of our promised goals over these short time scales and then over longer time scales to make sure we're ensuring long-term viability of our safety solutions. This solution will potentially go into the visors, which is one of the CubeSat missions that we are currently working on in the lab as the active spacecraft collision avoidance system, and could potentially be extended into larger systems of spacecraft in the future. And that is all. Thank you.